Okay, let's look at the notes here for 5.6. So to start off with, we're going to look at composite functions. So the first thing that we're looking at is a composite function. So essentially what a composite function is, what a composite function is for us is we can define it as a new function created by substituting one function into another function. So let's start off with looking at our first problem here. So we're going to see, the way that we know we're using a composite function is whenever we see one of two things. We'll either see it written in one of these two ways, g of f or g of f of x, right? Same thing. Okay. So that would be g of f. Okay. So we have two functions here, 2x plus 3 and x squared. We're going to start off by, we look to see which one goes on the outside. So seeing that we have the g's of furthest most one on the outside, or furthest most function on the outside, that's going to be the formula that we're going to be using. So we start off with our, we'll say, g of x is equal to x squared. We're going to plug in, instead of writing x, we're now going to write f of x. So g of f of x is equal to, instead of writing x, we write our f of x in parentheses squared. But that doesn't really help us anymore, right? We know what the value of f of x is, or relatively. If we look over here, the formula is 2x plus 3. So we can instead choose to write this as 2x plus 3 squared. And we could break that down to go farther a little bit with it, but it's not necessary for this. So 2x plus 3 is equal to g of f of x. Now let's try the same thing for f of g of x. Now, for f of g of x, this time we're starting off with the formula for f of x, which is equal to 2x plus 3. We're going to be plugging in g of x instead of x, so 2 times g of x plus 3. We can replace g of x with x squared. And finally, combining this out here, we get 2x squared plus 3 is equal to f of g of x. Now, let's look at an example that kind of helps us see that as well. So, looking here, we're going to, they give us two functions. They want us to find the f of g of x and the g of f of x and evaluate them for the given x value. So let's focus on this one here on the left side. So 2x plus 3 is our f of x, and g of x is equal to 3x minus 5. So we'll start with the f of g. This would be the same thing as, so we start with the 2x plus 3. We're going to replace the x with the value of g of x. So 2 times 3x minus 5, and then the plus 3 from the original problem. We can distribute the 2. We get 6x minus 10 plus 3. And finally we get 6x minus 7 is our f of g of x. Now we can, we can write this out here. Let's find the value of g of f of x. So g of f of x is equal to, we start with the 3x minus 5. We're going to replace the value of x with f of x. So that gives us 3 times 2x plus 3 minus 5. Distribute the 3. 6x plus 9 minus 5. 6x minus plus 4. is equal to the g of f of x. Perfect. So we met the first condition. We found our two formulas that we're going to use. Now we're going to replace the x on those with the value of 1. So we get 6 times 1 minus 7, which is 6 minus 7, which is equal to negative 1. For the g of f of x, 6 times the 1 plus 4 is equal to 6 plus 4, which is equal to 10. And that's how we evaluate those kind of functions. Next part that we're going to look at here are our inverse functions. So our inverse functions are essentially, they're going to be a function that, let's put that down, undoes another function. So an inverse function is a function that undoes another one. So what that looks for us, how we're actually going to find this inverse. There are essentially two, we could say 3 steps. So to find the inverse, the first step is to swap the x and y variables. Now, looking at our x and our y variables, okay, it's hard to see there. You look at this problem, f of x is equal to 2x plus 1, and you don't see a y. Okay, you don't see that y written anywhere. Now, this is where you need to remember that f of x means the same thing as y. F of x is equal to y. Okay, that's important for this. So looking at this, this is really the same thing as y is equal to 2x plus 1. Now, we follow through with that first step. We swap the x and the y. So we just physically swap where the variables are. We don't move anything else. So if I swap them, I get x is equal to 2y plus 1. Now our second step is to solve for y. So in order to get the y by itself, I would subtract 1 from both sides. I get x minus 1 is equal to 2y. Divide by 2 on both sides. Now both of these are getting divided by the 2, not just one of them, so be careful with that. We get y is equal to, we can say, we'll just call it 1/2 x minus 1/2. So we get the minus 1/2 from here. There's really a 1 in front of the x, 1 over 2, and so we get that 1/2. So y equals 1/2 x minus 1/2. Now we could do the same thing with, say, x squared here. So with x squared, we get y equals x squared. Swap that around. X is equal to y squared. To undo it, we take the square root of both sides. Those cancel out. We get y is equal to plus or minus the square root of x. So that's just how we find the inverse just given the function. So just given a function, that's how we find the inverse. Now say we're looking at a graph. They give you a graph. The way that we do this to test if it's a function, well, test if we're going to test if the inverse is actually a function. Okay. If you remember from previously, right, when we were working with just those kind of equations and determining if an equation was in fact a function, right, we used the vertical line test, right, where we passed it vertically through the graph. If it hit 2 spots, it failed and it wasn't a function. Now with the inverse, it's going to be kind of flipped. So instead of doing vertical line test, we will pass a horizontal line to determine if the inverse is still in fact a function or not. So if we look at this first graph, if I passed a horizontal line across the entire graph, I can only ever hit 1 spot at a time. But on the second graph, I could hit multiple spots, right? I'm going to hit 2 spots here. I could hit it down here, right? There's a number of ways that we could do that. So this is why this is not a function, and this is a function. Next one is, let's look at this. We're going to graph this. We're going to graph an inverse. So let's start by graphing just the original problem. Now, this original problem is in the form of y equals mx plus b, where m is our slope, which is going to be our rise over run, and b is the y-intercept. Okay. Graphing this, I'm going to turn this slope of 10 to be 10 over 1. So I know that I'm going to start here at 0 since I have no y-intercept. So I start off at 0. I'm going to go up 10 over 1. Put a dot there. This is the graph of the function as it is. Now if I want to find the inverse, right, I swap my x and my y, so I get x is equal to 10y, y is equal to 1/10 of x. So that says I'm going to go up 1 over 10. Okay? So that's what our graph would look like. Now you could reduce it, shrink it down, scale it down, so you could graph the whole thing a little bit better, but that's up to you. I will also point out for those that if I were to graph the line y equals x, that line, our inverse and our original function are perfectly symmetrical over that line. Something else that's kind of important to note. Now, looking down here, we want to determine if each of these pairs are a function or not. So the way that we can tell if these are functions are whether or not, if I flip the x and the y values, so if I swap these around, that's what this should look like. So I replace the x and the y, I flip them around, just like I did up here. So I got -1 and 1. So that one's good. Look at the next one, 2 and -2. When I flip it around, I get -0.5 and 2. So there's an issue going on with these. So are these inverses? The answer is no, because they're not flips. They should flip every time. For our final ones here, okay, I'm just going to kind of cheat this one, change that. So, looking at this, right, we can check to see if they flip. We get -4 and 17, 17, -4, -3, 13, 13, -3. So you'll notice that each of these now should match. They should be inverses of each other, right? They're flips. So is this an inverse? The answer is yes. Looking at these last two graphs, we were going to use determine, hey, these are inverses, that's what they tell us. Determine if they are a function. We pass our horizontal line through it, this one fails. If we pass a line like that, it hits 2 points. So no, it fails the vertical line test. Or, sorry, horizontal line test, my mistake. The same with this. I could pass a point right through there. Hits 2. I could in fact hit 3 points if I wanted to. So this one is also no, it fails. And that would be it for these notes. So these notes were just finding the inverses for functions, graphing those, and then also substituting one function into another. If you have any questions, you can leave them down below, and I will try my best to get to you. Thank you.